Here I'm going to demonstrate drawing the graph of an exponential function such as y equals 2 to the x. We'll want to use the table method. We will plug in a negative 2 for x. That's going to give us 1 over 4. 2 to the negative 1 will be 1 over 2. 2 to the 0 is 1. 2 to the 1 is 2. And 2 to the 2 is 4. Now I want to try to plot those points. And I'll just do one more here. Alright, we can see the curvature of it pretty well now. I'll just try to connect them with a smooth curve. There we go. Below are a few functions of the form y equals b to the x, where b is a different base. The one that I had just drawn was y equals 2 to the x. And that is one of the curves on here. That's actually this one right here. 2 to the x. I can tell because it intersects the point 1, 2. This next one here touches at the point 1, 3. That makes this 3 to the x. It's a faster growing exponential function. And then this one here is actually 4 to the x. So as you can see, they share some things in common. All of these exponential functions do pass through the point 0, 1. That's significant. Also, we see the larger the base is, the steeper the function is, and the faster the growth of it will be. Here are some exponential functions where the base is less than 2. It's between 1 and 2, actually. Those fractions are the numbers 2, 1.5, 1.33, and 1.2. So let's label them. 1.2 to the x has the smallest growth, followed by 1.33 to the x. Then we have 1.5 to the x and 2 to the x. Now, can we find what is called the limit of the function? The limit of b to the x as x approaches positive infinity, where b is an integer greater than 1. So what is the height that these functions are actually growing to? Well, they're all growing to a height of infinity. Now, what is the limit of the function b to the x when x is headed toward negative infinity? That's going to the left. What are they headed toward? 0. So on the right side, they're growing without bound. On the left side, they're heading toward an asymptote, where their y value is heading toward 0. Now these are examples of exponential growth. It's exponential growth because the value of the function is increasing as x increases. But these functions are actually an example of what we call exponential decay. Now, what type of situations would we expect for each type? Well, we would expect exponential growth for the spread of diseases and viruses. And that's a big issue today in 2020. Also, we expect exponential growth for the growth of any kind of animal population that's growing with a lot of resources and few predators. Also, the spread of information within societies. When it comes to exponential decay, examples of that would be examples of exponential decay could be the loss of value over time, depreciation. Exponential decay can also model the way that demand decreases with increasing supply available. Also, within the realm of science and physics, it could be the decay of current once a circuit is shut off, for example. All right, so let's go ahead and try to label these. What are the bases that are involved? There's 1, 0.8, 0.75, 0.66, and 0.01. All right, well, when the base is 1, 1 to the anything is itself, so the horizontal one is actually the function 1 to the x. This one here, the next yellow curve, is 0.8 to the x. The green one must be 0.75 to the x, and the blue one is 0.67 to the x. And this one, the most extreme curve, perhaps, is 0.01 to the x. So what is the limit of this function as x heads toward infinity when the base is less than 1? It doesn't actually have to be an integer. That's a typo. Find the limit of the function as x heads toward infinity when the base is less than 1. The limit is 0. Next question is kind of interesting. It says, can you express the exponential decay function with a negative exponent instead of a positive one? So if we take the original function 1 to the x, that's just itself. But 4/5 to the x could be rewritten as 5/4 to the negative x. Three-fourths to the x is the same function as 4/3 to the negative x. 2/3 to the x is the same as 3/2 to the negative x. And finally, and if you graph the function 1 over 100 to the x, you'll find that it's actually the same function as 100 to the negative x. The point is that there's more than one way to represent the same curve, and it is possible to have a negative in the exponent of an exponential function as well.